she will very likely bring some. Just so you know, so you'll be able to buy some if you're prepared if you want to buy some plants. Okay.
So without further ado, I'm going to hand over to Becky. Over to you.
Thank you. I think some people are on Zoom, so I hope they can hear me okay. Fingers crossed. Right. Yeah, hi everyone. Thank you so much for coming. I'm Becky. My mom lives around the corner, but I'm up in Glasgow at the moment, so come down today, and I'm doing my PhD in chemistry, and I'm trying to just sort of roughly explain the basics of the background of the research I do and a little bit about sort of the main principles, and hopefully it'll make sense. But if anything is going over your head, or you just want me to go over something again, just please like put your hand up, because I'd rather everyone was like with me rather than holding questions. Obviously I'll have more questions in depth at the end, but if anything you just want, again, just shout, because then it's better for everyone. So but hopefully it all makes sense to everyone. So I'm going to be talking about smart windows. So the work I do is to try and find a new way of doing smart window technology. But before I go into all that, I'm just going to start with what smart materials are. So smart materials are materials that respond to external stimulus. So that can be heat, that can be pH, that can be light from the sun, it could be electricity, it could be anything. And there's lots of different products that you might be familiar with. This one's not very common, but it's shape memory alloys, and those are smart materials because you can bend them, and then when you apply heat, they will remember what shape they were in before and they'll pop back. So this is an example with some glasses, but I don't think these are very commonplace. Another example, which is something that everyone can do at home if they really want to, which is, I think this is cornstarch and syrup, water, sorry. And that is electrorheological, which means if you apply a current to it, the viscosity will change, so it will become more solid-like. So this is a balloon, and as the balloon gets closer and the static electricity from a jumper or something gets closer, it's aligning the particles and making it more solid. So you can see it's not flowing in the same way. But the most common form of smart material is what I work with, and those are chromic materials. So chromic materials change color based on an external stimulus. So these are very commonplace. You probably have seen some of these products before. So if you have a pair of sunglasses that in the sunlight tint, these are responding to sunlight. So they are called photochromic because it's responding to photons in the sun. So something that changes color based on an external stimulus. Everyone's probably been given or has one of these mugs that when you make a cup of tea reveals a pattern or a picture or something, and this is responding to a change in temperature. So they're thermochromic materials, and these are the most commonplace materials, chromic, and they've got lots of applications in medical sort of products. So thermometers, or you can get baby grows that can change color if your baby's overheating. And they're really useful because people understand a color change. It's very non-verbal. They can see instantly that something is different. And if you know that that's a result of your baby overheating, you can immediately act. So they're very sort of powerful technology. Another chromic material that everyone is probably horribly familiar with by now is a lateral flow test, which, as you know, changes color to give you a result you might want to see, or maybe one that you don't want to see. And that's responding to a chemical change. So something reacting between your sample in the bottom and something in the strip. But what I work with is electrochromic materials. So they change color based on application of a current. So you connect a power pack and it puts voltage through it, just like a light bulb, and it changes color. And it does that because you're changing what we call the oxidation state, or the charge. So the way I've tried to explain it is, people say they're feeling blue, or like happy is a yellow color. So each individual, at the amount of charge you have. So, you know, if you have a magnet, you know that there's a negative and a positive side, same with the battery. So the different amount of charge there is, each different state or each different charge will have a different color. And that's the principle that these kind of systems work on. So the application is smart windows. So smart windows, you may have seen, they're not very common. I think they're sometimes in aeroplanes, but they're basically a window that you can press a button and it will tint on demand. And the application for this is if you wanted like privacy, you can just flick a switch and your meeting room will go dark, or if you're in a car and you've got a taxi divide, something like that. But another application is just for controlling your building costs. So if it's a really sunny day and it's really hot in your office, but then you can essentially apply a big pair of sunglasses to the outside of a building, you can reduce the temperature, you can affect air conditioning costs, lighting costs, heating costs, things like that. And there's a lot of different studies, but the main things are in bold is that between 25 to 50% reduction in costs from some systems they've tried out. And that obviously is good because you can get really efficient buildings, you can save on money, but it's also good for the planet because you're not using as much energy as you might have been. So that's why we want to do the work, because we're potentially making buildings more efficient, which is great. And windows are the biggest heat loss of a building. Like that's why everyone gets double glazing, because you want windows because you can see out and you don't want just a brick wall to work in, but obviously they are losing heat. So we want to make those better. We want something that goes from completely transparent to completely black or to gray. That's really hard to achieve because there's a visual spectrum of light, and for something to switch between those two colors, it would have to absorb all of the visible region of light and also none of the visible region of light on demand. So that's quite hard to achieve. So usually we see things like this where that isn't quite transparent, it's more yellowy, bluey tinted, or we get something like this, which isn't black, it's more blue. So my work is looking into organic molecules, and these are just molecules made up of mainly carbon and hydrogen, and they're an alternative to things with metals in. And the reason we're trying to do that is because metals are mined from the ground, they're expensive, they're going to run out at some point, and metals are really useful for lots of other things that are more essential, like everyone's phone has precious metals in them, and that's more important to society than windows are. So we're looking to move into organic chemistry instead, which is where my research comes in. They've got lots of advantages. So they can give you really intense color. They can change between states really fast. They're tunable, which is what this talk is about. They're very easy and cheap to make. And crucially, our systems are water soluble. So if you're gonna replace every window in your building with something, you'd want it to be water soluble, because anything that's going to be a potentially harmful solvent is just going to be dangerous to the public. So, and water is cheap and bountiful, so we want something that's water soluble. That's really good. So we're using organic molecules, as I said, so carbon and hydrogen. And you don't need to understand too much about this, but we work with these systems that are called naphthalene diamides, or NDIs. That's what the chemical formula looks like. But all you really have to understand is these three parts that I've colored in. So that group there, so this is sort of a representation of this bit here. This bit in blue is that bit in blue. That bit helps with water solubility. This red bit here, that's something we can change really easily. So we can take that off, put a different group on, just by changing the way we do the synthesis, but that is very easy to take on and off. And then we have a big thing in the middle, which allows the molecules to do something called pi stacking. So pi stacking, because it doesn't look so much like this, because this is sort of looking above, but if you look at this molecule from the side, it would look a bit like this. So this bit here is this bit in the middle, and then these bits are sticking out from either end. And that bit in the middle is really, really flat. It's very rigid. It's got a lot of electrons in it, which allows it to interact with similar things. So it will kind of stack on top of itself, a bit like this, which you can imagine as just like a stack of plates. So it's just stacking and stacking and stacking, getting bigger and bigger and bigger, and then eventually they'll start to fold in and make interesting structures. And because there's a lot of bonds in this middle bit, so there's a lot of so if this is water, so oxygen and 2 hydrogens, so that is made together by like electrons interacting, and that's what makes a chemical bond. So there's lots of bonds in the middle, lots of electrons in the middle. So electrons can almost move down the stacks as well, which helps with, if you're doing something that's with electricity, it helps with conductivity. These two things, the blue and the red group, can affect the structure. And I'll come to that in a second. But first off, how does it work? So we take our solution and we put it into 2 pieces of glass. I have one. Yeah. So the 2 pieces of glass and our solution's in the middle. There's a bit of a bubble in that one. And when we apply a current, it sort of forces the electrons through the middle. So it's going through the top, it has to come out the bottom. The only way it can go is through the middle. And that has the effect of doing what we call reduction. And that means it's giving an electron from the power source to the molecule that it shouldn't have. A good way to remember that is something I did at school, oil rig, which means oxidation is loss, reduction is gain of electrons. So reducing something, it's giving it electrons. Oxidizing something is removing electrons from it. So we're giving it electrons, so we're reducing the molecule. And that electron shouldn't be there, but it's fine because, as I said before, that middle section is full of electrons anyway, it's full of bonds, and what happens is it kind of sticks around the middle, but it doesn't ever stay still. It's always moving around that middle section, and that's how it remains stable. And that system with an extra electron is really, really highly colored. And that's what makes the color change. So the more of this we make, the more reduction that happens, the more molecules we have, the more intense the color change. And that's the principle that the work is based on. And luckily for us, you can reverse it. So if you apply a slightly different potential, we're going to do the opposite, and we're going to take those electrons away, and we'll reverse the color change. So that's the basic principle of what this work does. And this is what it looks like. So I'm going to try and do a proper example in front of you. Hopefully it works. But just to show you the difference, so this and this one on the right is 10 times more concentrated than this one on the left. So that's why it's much darker. So we can really easily tailor the color by just adding more and more in. So hopefully, if everyone can see this, it should change color. So can everyone see that? There we go. Yay. So if I leave that on for a bit, it should keep its color long enough to be handed around. Sorry, the glass is a little bit dirty. Leave that one going. Got 2. So it's very fast color change, which is great because that's what we want. So at the start of my PhD, I set out to create, if we were going to make the perfect system. So this, because it's very hard to achieve, as I said before, it's been referred to as the holy grail of electrochromics. And this is what we want. We want something that looks normal under normal circumstances, and then when we apply a potential, it changes color. So we set out the criteria. If we were to make the perfect thing, what would it be? So we'd want it soluble in water. We'd want that color change, but we want it to be as dark as it possibly could. We'd want it to be as fast as it possibly could. We want it to be able to be used a lot. Obviously, we don't want it to be just one and done. Because this is an academic venture, we wanted to really understand the relationship between structure and color. And I will. So, the whole reason we're asking this question in the first place is because of a concept called self-assembly. And that's pretty much what it says on the tin. So we have lots of molecules in solution, and then either spontaneously or in result of a trigger, like pH or temperature, these molecules will assemble by themselves into a complicated structure. So as I was saying, we have those stacks. Those stacks will then eventually fold in on themselves, and that's what the whole point of the stacking is itself self-assembly, because we're not doing anything, it just happens naturally. So the important thing is, I'll go back to my water again. So chemical bonds between hydrogen and oxygen make water. That's not what's going on in these structures, not a chemical bond. Instead, it's more of a vague interaction of charges. So things that are negatively and positively charged will attract, things that are negatively and negative will repel, and those are the principles that really hold together self-assembled structures. So there's a few different versions of these. So hydrogen bonds are just basically something has lots of electrons like oxygen. Hydrogen doesn't have many, so there is an interaction there, because if it has more electrons, it'll be slightly more negative, but it's not a proper bond. Hydrophobic and hydrophilic, that's the chemistry that's used in things like detergent. So this group here, the blue one, that's something that really loves to be in water. And this long tail is something that hates being in water. So if you have oil on your plates, you use something like this to sort of bridge the gap between water and oil, because it'll assemble like this. So all the water groups will want to be in the water, and then this will all be in your oil. And that's why you get sort of foam when you wash up. It's this sort of thing happening. And the last one is a kind of interaction called van der Waals, and you don't really need to understand this, but it's based on the principle that if you have a nucleus with electrons around it, that's like a standard atom, and that's what you see in textbooks, but it's not quite true in reality. The nucleus is slightly off center, and because of that, you create a very small polarity across the atom. So this then is going to be more negative because there's lots of electrons. This then is more positive. And that's fine until they move close together, and then there is a little bit of interaction. So basically, because these are very vague forces, they're very easy to break. So if you change something like pH or temperature or solvent, you can break these apart very easily, much more easily than breaking a chemical bond. Like you can boil water and it will create steam, but it's still chemically bonded in that steam. So it's much, much, much weaker. You can also potentially change if you put something in that has a hole. You'll get guest host interactions, which just means if something will fit into a hole, naturally it probably will. So you can really easily tailor these things is basically what you need to get across. And that's what I was trying to get across with my title picture, because we can change the structure, we can change the self-assembly, we can break and make those bonds as easily as changing a post-it note on a board, because we can change this group, that's the red group we talked about earlier, we can change that, we can change the charge of the molecule, and that will affect structure. And we wanted to know, how does that affect that color change we just saw? Can we make it better? Will it make it worse? Just wanted to understand a little bit more. So if we have our solution and we want to look a little bit closer, there's a few different things that could be happening. So we can have molecules that don't care about each other, just scattered, not interacting. Or we can get that stacking that I talked about earlier. And they all stack into, as I said, really long fibers that then can fold and make something like this, which is a cylinder. There's a variety of different structures that it can make. If you have a lot of these kinds of fibers and they start to entangle with each other, then you form really, really big scale structures, and that can potentially make the solutions become more solid-like. So gels are based on this kind of chemistry. So that's something that is mainly water, but if you turn it upside down, it won't flow, it will stay. So lots of makeups and creams are based on gel chemistry. So as I said before, you can really influence the structure by changing pH. And all pH is a concentration of this thing here, hydrogen plus. So if you have something that is low pH, like lemon juice, that just means there's a lot of H plus ions in it. And opposite for high pH, something like bleach, that's got a lot of OH minus ions in it, and water's somewhere in the middle. But basically all pHs is a measure of that concentration. So we can change that because we can add acid and base very easily. You can do it in your own house, so it's very easy to do in a chemical lab. And what happens when we do that? So if you imagine this is something at very low pH, the less and less H plus there is, so the more and more base we add, it's going to want to take some of the hydrogens of this molecule. And these ones are the easiest to take. So it will take one from each side. The more and more base we add, it will take these hydrogens. And the molecule is fine with that, but it's still lost something. So it gains a negative charge. And all that means is we're adding more and more negative charge. And we're adding more and more negative charge into the solution as well. So we're getting a lot of more and more negative. And that's like magnets. If you get too much negative next to each other, they'll be unhappy and eventually repel. So if we keep putting more and more in, we're going to break apart those stacks, we're going to break apart those structures, and we're going to get something more like dispersed molecules that don't care about each other. If we go the other way and go too far down pH, we're adding too much positive charge in, that will just crash out of solution. It will just become a clump of solid in the bottom because it's just not stable enough anymore to be soluble. And what happens is as we lower the pH, that's when we start to form these stacks, that's when we start to form these structures. And rule of thumb, high pH, they're not interacting with each other, and low pH, we get more complicated or at least larger, just bigger structures because there's less charge to repel the individual molecules. For this kind of system, that happens around pH 6.5 and 9.5. So that's just a measure. We go from about 12 to 6. And that's the point at which these things start to change. And it's all based on what the charge is at these particular groups. So it's all based on that. And there'll be either a small or a more significant change in the kind of structures that these molecules want to make. And we wanted to ask, does that affect color? And the simple answer is yes, it does. Because you can see this is low pH, this is high pH, the blue line. There's nothing happening, it's very, very low color. I don't know if you can see it by eye, but very, very weak color, very intense color at pH 9. So we found a way to get almost 10 times the color from the same solution just by changing pH. So that's great because we can make the system as efficient as possible. We can maintain that really easily. So that's great that we can do that, but we want to understand why. So to do that, we use this technique called small angle neutron scattering. And all you need to know about small angle neutron scattering is that you have to go to a very big place in Oxford to do it. And it tells us about structure. And if you want to be slightly technical, we take hydrogen atoms and we whiz them around a big synchrotron, a bit like the Hadron Collider. It just whizzes things around very, very, very fast. And when they're fast enough, we fire them towards our sample. And it will hit something that will expel neutrons when it's hit by a really high energy particle like that. And these neutrons hit our sample and they will scatter off it. And the way that it scatters into a detector will give us something that looks a bit like this. And we can fit that to theoretical models, and that's how we get the information. So we can change the parameters and find what fits best, but we basically can understand that level of size. So bigger than a molecule, smaller than something like a virus, but dead in the middle of what we would want. So taking all that information and fitting it to lots of models, we get this outcome, which is, this is color intensity. You can see it's really high at pH 9. So at pH 6 and pH 9, we form cylinders. So all the molecules arrange themselves into cylinders, but at pH 6, they're much more flexible than they are at pH 9. So the structure needs some rigidity to get that color change. And that's because these kinds of structures where it's a little bit more rigid support that radical once it's formed. So once it's formed that colored species, it's more happy to stay around when it's in that slightly more rigid shape. At pH 12, we don't form cylinders at all. We form almost like sheets that aren't really interacting with each other. It's just, as I said before, kind of dispersed stuff. And you can think about this a bit like Goldilocks and the three bears. So each molecule has something that it needs to be just right. So in this case, you need a cylinder, but it can't be too flexible. You need a little bit of rigidity. Oops, sorry. So you want the porridge to be just right. If you're going to take this metaphor all the way to the end, what about the other different? So as I said before, you can change the red group. What about all the other different options there are for different red groups? So this is another one. So I'll come to this in a second, but this is something else. I ran out of red balls, but that's something else that could go there. So if I was to take everyone from my group at work out to porridge together for some reason, everyone would have a different preference. Everyone would want different sweetness, different kind of milk, different toppings, and some people just wouldn't want porridge at all. So everyone has a different preference, and that's the same with these molecules. They've all got different preferences. So it's taking that concept of Goldilocks, but if you're wanting to consider every single factor, every single preference, then you would probably find something like the Holy Grail, because it would suit everyone first time and everyone would love it. But as we know, that's not the case. You can never find a porridge that's that good. So to look at four different, so all the time we've been looking at this green molecule here, and there's a few different ones we looked at through my PhD, and all you need to understand about these is that these top two are basically the same, but slightly different, like branches of a tree. That one's a little bit longer. The green one's slightly longer than the blue one, but they're pretty much the same. The bottom, we have these big rings. So this is what this model is. So compared to something like this red one, it's kind of branching like a tree branch. This is very sturdy. It's very big. It doesn't want to move. So if you think about these as Popeye's arms, because they are coming off the molecule, they're really big, they're really bulky, they're going to get in the way, basically. So that's why we wanted to look at these. We wondered if the preferences of these kinds of groups that are big and bulky are different to these kind of tree branch kind of things. So they are. So before we see that shape, it's pretty much the same, but these big bulky groups, they perform best at really low pH. And that's because the preference is different. The color's also different. So that brown one here, it's a slightly different spectrum, but the main point is that it's brown, whereas all the others are purple. And that's entirely based on the kind of structures it forms. So this is the brown one here. This is the group, and this atom here, which I've made black, there's nothing coming off it. So we get more flexibility. So this whole group can like rotate round, it can move. So we're offsetting all the rigidity of this. So it forms way more flexible structures than any of the other four. And that's why it makes a different color. So it makes brown color purely because of that atom, which is really interesting. And the bottom two, as I said, their preference is different. They just want to be as big as possible. So everything at the top wants to be rigid. Everything at the bottom just wants to be big. It doesn't care about flexibility so much. It just wants to be big and big and bigger. And that will stabilize that color. So if we go back to the idea of a dinner party with everyone with different preferences, you can't always please everyone, and someone's going to be a fussy eater that doesn't like anything. And in my research, that is this molecule here. It's the same as that one I was just talking about, but we put a big bulky group on that carbon atom that gave us all that flexibility. So we've stuck something on that's going to make it harder and harder to form those stacks. And because of that, it doesn't form those stacks. They're in the way, they can't get to each other properly, and it's just not worth the effort, so they won't do it. And we get this kind of structure, like at high pH, we get very dispersed molecules. They're sheet-like, they're not forming cylinders. They're not forming nice structures that can fold and self-assemble. And because of that, we get very, very poor color for this particular system. So just by adding one more thing onto the top, we've ruined it completely for ourselves. We're getting no color at all. We can't use these for windows. And it's also very hard to make because it is so big. So it's a lot of effort for no reward at all. So yeah, so as you see, there's hardly any color at all in this system. So just by thinking about that, we are thinking about how we can almost design these molecules to be as good as they can be. And by understanding their preferences and understanding how different kinds of groups or different kinds of structures like these affect those preferences and affect their ability to form that color, we can, in theory, create the best system. So just to conclude, structure affects everything. So it affects lots of properties I can't even go into because that was 4 years of my life I've looked into these, so there's a lot of other things to talk about. NDIs are fussy eaters, they have preferences, these preferences are different, and some of them just can't be pleased at all. So we have a lot to think about when we're designing structures, when we're trying to think of great water-soluble alternatives to mined metals. There's a lot more idea about design in this field. So we, instead of thinking about just a cut and paste, exchange this for this, we can think about tuning these a lot more, which makes them quite interesting. And if I go back to that criteria I had at the start, so at the end of the PhD, we decided that we've ticked off some things, so things in green. It is soluble in water. We got that color change, it happens quite quickly, you all saw it today. Cyclability, I didn't go into. It's okay, it could be better. That's something we then looked to try and make better by adding in lots of other things. And all the things in bold, so the color, the intensity of the color, the time it takes to switch, and also the cyclability, they're all affected by structure. And so we have started to understand that relationship a little bit more. Obviously, there's always more you can do. So maybe we didn't find that holy grail that we wanted, but we found some things that we didn't like. We found some things that didn't work, and we found some preferences for 4 different systems, which have a lot of potential in the field. If anyone is really, really interested in this and would like to read a very scientific paper about it, we just published this work, and come talk to me, I can give you a copy. But it just goes into what I've been over today in a lot more detail. But just to give you an idea about where this research could go next, which is quite exciting. So if we wanted to, we could look at every single red group. We could change this to be hundreds of different things. We could make it longer and longer and longer and just go on forever and find out the preferences of every individual system, which could be interesting. You might find a perfect one, but it's a lot of effort and you might not get that. Or you could take what we've already found and we could look at it in a different way, which I think is more interesting. So we can look at these as gels or films. And I've been doing some work recently where we grew the gel on a piece of glass, so a bit like this. And when we've grown it, so it's stuck to that surface, we can then apply a potential and change the color. So that is interesting because if we can grow stuff on the surface itself, we could grow a really big window really quickly, and that would be better than fiddling about with filling it with water. So that could be an interesting way to go. Also, if you're taking something like a flexible film or a gel, the diffusion is going to be different to the way it is in a solution. So you can do something called patterning, where we'll scratch out that bit of the conductive layer on the glass. So when we apply the potential, that bit doesn't change color. And if your diffusion is slower, it will hold that shape really well. In a solution, it falls apart pretty quickly, but in a gel, it will hold that. So that's quite interesting, because maybe not for smart windows, but for things just like devices, displays. If you were working in a corporate environment and they wanted to put their logo on the window as it changed color, like it has applications for that. So that's like a different direction you could go with the research, which is probably more interesting than just ticking off boxes. Yeah, so that's just a little bit about what I do. I'm happy to answer any questions anyone has or go back over anything. And obviously we've got to give thanks to the people who helped along the way, so everyone in my research group and our collaborators at ISIS and all the funders that helped me with my PhD at Glasgow, and of course all of you guys for coming out and listening to it today. I hope it's been interesting. And yeah, so thanks for listening. That's me. Does anyone
How long will it be before we see some of these sort of work that you've been doing actually practical solutions to problems?
It depends. So we did have some industry collaboration with someone who I can't say who it is, but they looked at building a prototype, and so the ones I had passed around today, they're 10 by 10. We scaled up to 30 by 30 and got that working, and they took it away and hopefully do something with it. But the problem we're having is the bigger we go, the more resistive the glass is. So we're having to put much more power through it. And that's something that if you took it away and an engineer could look at it and be like, this is how you make that better. And this is how you reduce the resistance. This is how you get the power bigger. But we can't do that in a lab. So it definitely needs someone to come in and just take it and do something on a bigger scale. But I think this is one alternative. This is one organic alternative. There's lots of others as well. So I think it does have the potential to come in. It's just whether they invest in it. I reckon it could be commonplace, hopefully in the next 20 years or so. I'm not sure, but it's really working out the long-term use. I think it's the only stumbling block at the moment, because it will. Some systems, not so much these, but some degrade as you use them. So we're trying to find more stable things, and mine are all solutions. So obviously those can leak. So you maybe want to move towards something like gels because they won't leak as much. So if someone was to throw a stone through the window and it smashed everywhere, like that wouldn't be great if you have solution leaking out. So I think it needs tweaking, but the principles are there. So it's really interesting.
Mix your chemicals with gelatin and make them into a gel? Yeah,
the only thing, so we've tried to do that with not with gelatin, but with a different thing that forms gels, and we saw improvements in cyclability, but every time we add something in, it might potentially affect the way they form structures. So so when you have stacks, you can either have stacks of all of A and all of B, not caring about each other, but you could also get ways like A, B, like or randomly or different orders if you get the gelatin even like coming in the way. So if you're disrupting that stacking, you might not get as good conductivity through the system because it relies on like that electron moving through the stack. So you can do it, but you have to really think about whether they'll disrupt each other and what effect that might have, because obviously structure has a huge impact on color. So it's trial and error a little bit, but we did get some interesting results from that. Yeah, sorry, you had a question.
Say that the glazing companies or anybody else tried to do this, you know, no doubt failed maybe, or maybe not, or couldn't push it any further and had to let it go? Has it got a history of any length of time trying to do this?
Yeah, so I think it's coming, they first noticed that these molecules did this color change. There's papers from the 60s even looking at these. In terms of using it for devices, that's maybe more like the 2000s. It started to become more interesting because people used a lot of metals before that, because metals work really well. Because metals can also form 5 or 6 different states of oxidation. So you could get something that forms 5 different colors from a metal. But now we're starting to think about greener alternatives, and metals are running out. So this is sort of where the shift of focus has come, maybe in the last 10 years or so. And you can, like, some first class planes, I think, do have them in the windows, but I've never seen one. Someone in my lab apparently saw one on his flight home, but they're always blue. They're like based on a metal that turns blue, and that's very, very good, and it's pretty efficient, but ultimately it's hard to source on a really big scale, so that's why you can't coat an office block in it. Whereas this stuff you can get from more sustainable sources, and we can make on a bigger scale really easily.
What would be the lifespan of it?
So it's pretty stable. So I've left it in the lab, in an oven, a fridge, out on the desk for, I think, for about 4 months, and we didn't see any degradation at all, in solution or solid. So, and the problem we're having, so when we cycle it and use it, if we use a technique to show us about whether it's degraded or not, it hasn't degraded. We think there's something like, if you have your 2 pieces of glass and you're reducing at the top, if it moves away and it's not at the top, and you can't take those electrons away anymore, and there's still some colored stuff at the bottom, then you've got charged molecules that you haven't quite got rid of, and the more and more of that builds up as you're cycling, it could change the structures. So we're seeing a drawback in the long-term use, but we think it's because of that rather than degradation. It's just, it needs to be kept at the top where it can be efficiently used and turned on and off, whereas at the moment we think it's sinking to the bottom, and that's a problem. But that's why we added in a gelator, and it did have some effects. But again, that's something that a better engineer than me could probably look at that and be like, this is what you need to do. It's really simple, because if we saw a color buildup, the more and more we cycled, which we thought was degradation, but then if you take it out the window and give it a shake, it's back to normal again. So it is pretty robust, which is nice. It's just, yeah, it needs something else to keep the reduction oxidation as good as it could be. And the reduction's much more favorable. It goes really fast. Oxidation takes a few minutes. So.
Well, there was an American firm over a couple of years ago now that's developing a coating for glass, which will generate electricity off the light falling on it. Now, I don't know whether it's chemical technology or nanotechnology, but it would effectively turn your house into its own power plant.
Yeah, there's examples of that. So at the moment, there's a recent review out, maybe like this year, looking into systems that can do both. So you layer something like this and something that can do that. So you have something that can generate power as well as give you all the energy savings. There's also ones that that work, I'm not sure how, but they somehow are self-cleaning, or they filter the air. So you can get those benefits as well as the color changing. So there is a move towards trying to do a lot more with them to make them more and more attractive for people to invest in. There's also examples that are like that, where they generate power and they also change color, but that's in response to light rather than electricity, like the glasses that change color. So you could get that tint, but also, as you said, generate electricity. So multifunctional windows would be really, really interesting if we found the perfect kind of system for that. I think that'd be really good.
Make a nonsense of energy saving houses with small windows, wouldn't it?
Yeah.
Your main thrust of your talk was about using organic instead of metallic compounds to change these colours. We can learn an awful lot from nature, and I'm just thinking of these squid and cuttlefish that flash their colours almost instantaneously. Have anybody been looking at how that works in terms of maybe relating to the work that you're doing? Or
That's a good
I don't
question.
know myself, I don't know how these colours change. But,
that's a good question. I think it depends on like how those work. So I'm assuming that things that are from nature might be based on changes with like chemical chromic changes. So it could be they release an enzyme or a hormone or something that makes that color change, which maybe isn't understood, or maybe it's hard to generate synthetically without, you know, harming lots of animals. So it's I mean, then we're also discovering things all the time that we didn't know. Like I think recently they discovered that puffins' beaks are glow in the dark, or they glow under UV light for no apparent reason. Yeah, it might be that we find something that works great that we can synthesize ourselves.
When you see these things on, they can change their appearance in seconds, you know, to match their backgrounds and that sort of thing.
I know, it would be great, and it might even be something that we can make on a really small scale, but it's always you got to think about, can we make this on a huge scale to make it commercially viable? So there's lots of different factors, and we're just looking at like academic aim, but to look at it on a commercial scale would be something else entirely, I'm sure.
Becky, you do lots of work with gel. Can you have crystals?
Yeah, so you can get liquid crystal versions of these. They are more transparent to white, so they'll form a liquid crystal, I think, which will make it go transparent, and then when you don't apply a potential anymore, it will go sort of opaque, which is an alternative, but the energy savings you get might be offset by, if you want a window on like transparent and you're having to apply a potential all the time to maintain that liquid crystal structure, you might end up wasting more energy than you're actually saving. So that's why we want something that goes from, that is transparent with no one doing anything and then goes black. And the only reason we want black is because it's the most aesthetically pleasing thing that people kind of want. They want black and grey, it goes with everything. So there is a lot of sort of yellow to blue. Yellow to blue is what you see a lot. And sometimes green to red, things like that. But we were looking at just what we'd want for windows. But there are liquid crystal ones which are really interesting. There's also ones that respond to humidity as well. So if it's really humid, it will change color, which is hydrochromic. But then you've got to think, like, if it's a rainy day, will it change color when you don't want it to? Things like that. So especially in the UK as well, like, this is the problem with polymers. They can be really sensitive to water and sunlight, which you don't want in a window because it's going to come into contact with all of those things. So yeah, trying to find, it's different people might want different things from their products. It just depends on what each criteria is, I think. Yeah.
Yeah, the connection with camouflage.
Yeah, I guess it depends on what color you're trying to achieve. So you can get a lot of variety in organic chemistry. So you can get reds, greens, yellows, blues, purples. So if you were to make something that was a sort of combination of all of those things, maybe you could get something like camouflage, but it just becomes very complicated the more and more colors you add in and the more and more sections. So sometimes people make things with layers, so you can layer the different colors together and tune it that way. But yeah, it depends what you want out of it at the end of the day. I think if you throw enough money at it, you probably can. But people are maybe not throwing money at this area so much as they are at other more important things. So we'll see where it goes, but it could be interesting, I think.
I don't know about the rest of you. I was along with thinking about cuttlefish and thinking about sort of communicating and the different things you could do. And then camouflage, imagine a building disappearing. And it's just amazing. It really has got lots of scope, hasn't it? It's got lots of different uses, and it's really our only imagination. Sorry, no, it's only money that will hold things back. But on behalf of the society, I think we'd all like to thank you very much for that talk. It was really interesting, something very different, and hopefully is sort of our minds working a lot. Yeah. Okay, so if we could put our hands together again.